All right, let's jump right in. I came across this incredible new paper that asks a really simple but kind of profound question. What if we could build an AI that separates its ability to think from its need to know things? It's a completely new way of looking at artificial intelligence, and honestly, it could change the whole game.
But first, let's talk about the problem this paper is trying to solve. We have these ridiculously powerful AI models, right? But they have this one very expensive habit. Every single time they come across a concept, even a really simple one, they burn a ton of processing power figuring it out from scratch. So the question is, why are these genius AIs constantly relearning things they should, just know?
So check this out. This table gives us a fantastic look under the hood. For an AI to figure out a simple phrase like Diana, Princess of Wales, it has to go on this whole journey through its internal layers. First, it kind of figures out Wales, the country. Then it starts to grasp the title Princess of Wales. And only then, way down at layer 6, does it finally put it all together. It's painstakingly rebuilding static factual knowledge every single time.
And this analogy just hits the nail on the head. Imagine a world-class chef, a genius, but every time they want to cook something, they don't just grab the salt. No, they first have to rederive the chemical formula for sodium chloride from scratch. That's basically what current AI is doing, especially with a popular setup called Mixture of Experts, or MO. These models are full of specialized experts, but they're wasting their brain power on the basics.
So this brings us right to the heart of the paper. How do we cure this expensive amnesia? The researchers had this key insight that our language models are really doing two totally different things all the time. There's dynamic reasoning, actual thinking, which needs computation, and then there's static knowledge retrieval, which should really just be about memory. So they laid out two different paths. On one side, you've got what we do now, conditional computation. That's our brilliant chef who has to think hard about absolutely everything. But on the other side is their new idea, conditional memory, a system they call Engram. And the best way to think about this is giving our brilliant chef a massive grand library full of every recipe imaginable. Instead of reinventing the wheel, the AI can just look things up instantly. So what's the technical term for this magic library? It's called conditional memory. It's a whole new architecture where the AI does what's called an O1 or constant time lookup. All that means is that it takes the exact same tiny amount of time to find a piece of info no matter how huge that library of knowledge gets. It's literally as fast as you or I looking up a word in a dictionary. It's just instant.
Okay, so you're probably wondering, how does this grand library actually work its magic? Let's take a look inside the architecture. It's built on a really clever two-step process that makes the whole Engram system tick.
It's actually a super elegant two-step dance. First up is retrieval. The system sees a few words, like Alexander the, and uses this lightning-fast hashing method to instantly grab the memory for Alexander the Great. In our analogy, that's the runner in the library, sprinting to the right shelf and grabbing the recipe card. Then comes step 2, fusion. A smart little gate looks at the context and asks, hey, is this memory actually useful right now? That's our librarian, giving the recipe a quick check before handing it off to the chef.
Now this is where the story gets really, really cool. The researchers started out just trying to fix a memory problem, but what they ended up discovering was something way bigger. The real payoff wasn't just about better knowledge. It was about better thinking.
This discovery led them to what they called the sparsity allocation problem, which is a fancy way of asking, if you only have so much brain power, how do you split it up between thinking and remembering? How much chef do you need and how much library? And what they found was this perfect U-shaped curve. The best models weren't all chef or all library. They were a smart hybrid of both. The sweet spot was in the middle. And when they dialed in that perfect mix, well, the results were just mind-blowing. I mean, they totally expected the model to get better at fact-based stuff, and it did. But the truly shocking improvements, they came from somewhere else entirely. First up, bam! A massive 5-point jump on the BBH benchmark. And that's a test that measures complex, multi-step reasoning. Next, a 3-point gain on human eval, which is a benchmark for writing computer code. And then another 2.4-point jump on the math benchmark. The model was fundamentally getting smarter at logic, coding, and math.
So this just leads to one giant question, right? How on earth does giving an AI a perfect, instant recall memory for facts suddenly make it better at reasoning? I mean, those two things feel like they should be completely separate skills, but it turns out they are deeply, deeply connected.
Well, the answer is something the researchers call a free brain upgrade. It's a great phrase. By basically outsourcing the boring job of remembering facts to the memory library, the Engram system frees up the AI's main thinking parts to focus on what actually matters, solving the hard problems.
And this map proves it. Now, don't worry, this chart looks complicated, but the story it tells is actually really simple. Just look at the bright diagonal line. See how it's shifted up and to the left? All that means is that an early layer in the new Engram model, let's say layer 5, is already doing the heavy lifting that a much deeper layer, like layer 12, has to do in the old model. They call it effective deepening. The model basically gets smarter without any extra computational cost. It's wild.
And here's the best part. It's incredibly efficient. This chart shows that you can tack on a gigantic 100 billion parameter memory library, and you can store that library on cheaper, regular computer memory instead of crazy expensive GPU memory, and the performance hit is less than 3%. This almost completely sidesteps one of the biggest bottlenecks in AI right now, which is GPU memory limits.
And that efficiency leads to another amazing benefit. Because the Engram memory is handling all the simple, local stuff, the model's main attention brain is freed up to focus on the big picture across really long documents. Just look at these scores. On needle in a haystack tasks, it leaps from an 84 to a 97. In variable tracking, it jumps from 77 to 89. It means the model can finally see both the forest and the trees.
So this all brings us to the final, crucial takeaway. The authors of the paper aren't just suggesting a small tweak here. They believe this idea of conditional memory is an absolutely essential building block for all future large-scale AI models. It's not just an optional add-on, it's a fundamental shift in how we should be building these things from the ground up.
Which leaves us with one last really big idea to think about. For so long, we've basically chained an AI's ability to reason to the information it can cram into its active parameters. This paper shows us how to finally break that chain, and it raises a truly massive question for the future of intelligence. If an AI's power is no longer limited by what it can hold in its working memory, what happens when that memory becomes, well, effectively limitless?